In this video, we're going to look into more measures of variation. Last time we were left with variance. Variance symbolized by, let's write it down here. Variance symbolized by sigma squared if it's population, or S squared if it's sample, cannot be an appropriate partner for the mean because this is in squared units. Squared unit. Therefore, to have an appropriate partner for the mean, let us take the square root of the variance, and that will give us the standard deviation. So the standard deviation is defined really as the square root of the variance and denoted by S if it's a sample and sigma if it's population. And the formula is as you can see below. For our running example, the variance and the standard deviation are given by the table in Excel. Do take note, however, that we have the standard deviation here, and what we have here is the sample variance. Microsoft Excel is in default that what we're looking for is the sample variance. Now, there are rules wherein there is a consideration in computing for population variance and for sample variance. In the formula that you've seen before, the denominator would be n minus 1, and n stands for actually our sample size. However, if our sample size will be bigger than or equal to 30, then this, and replacing it with just n, would be statistically the same because the size of the sample will matter. Now, since the size of the sample is bigger than 30, it will not matter if that is the case. In the case in our running example, the size of our n is 25, which is smaller than 30, which means when we compute for the sample variance and the population variance, the numbers would be quite different. You might be wondering, sir, how come there is a difference wherein n, we only use it for population, and n minus 1 for sample? That is to reduce the bias in the computation of this variance, which is beyond the scope of this course. But again, just to summarize that up, what Excel shows is sample variance because its default is using n minus 1. However, that sample variance can be considered as population variance if our n is bigger than 30. But in our running example, since it's not, then what we have is really the sample variance. And getting the square root of that sample variance will give us the standard deviation of our dataset. To interpret the standard deviation, we can use the general interpretation as follows. The variable of the sample units vary around or deviate from the mean by around the amount of the standard deviation. So in our running example, we would have the power of time of the phones vary around or deviate from the mean of that is 8.6 seconds by around 5.72 seconds. To further illustrate what this interpretation means, let's have a number line. Let's say that our mean is here at 8.6 seconds. Using the standard deviation, this means that the next value to the right of 8.6 seconds is 8.6 plus 5.72, and that is around 14.32 seconds. And then the value previous, the mean of 8.6 would be 2.88. Now, but we don't have those values. Yes, that is true. However, this just gives us a rough estimate that the distances between the mean and one specific value would be around 5 or around 6 if we're going to round it off, which would mean that the values around 8.6, even though we don't have that value, but our data set falls around the distances between the data set and the mean would be around 5 to 6. So theoretically, we can compute the other values as we just keep on adding 5.72 to the distances. So we can also say that the distance between this and the next value would simply be 5.72. That's how standard deviation would be. It's the distance of a specific value to the mean that we have. And since that is distance from the value to the mean, we can actually say whether the values, let's draw another one here, are actually closer to the mean if they have smaller standard deviation, or if they're bigger, then they're farther apart or more dispersed from the mean. Another measure of variation is the coefficient of variation. It is a unitless measure of spread and expressed in percentage, given by the formula below. So the formula below, we have S, that stands for our standard deviation. Standard deviation. Our X bar stands for the mean. Then this is times 100, then put the percent sign. So that's how we compute for the coefficient of variation. The coefficient of variation is used for comparison of spread of variables with different units of measurement. It is quite difficult to compare the height and the weight in terms of their variability because they are measured in different units. Hence, we need to use coefficient of variation to compare which one is more consistent, the height or the weight, in the context that you're studying it. So, we have already encountered 4 of our measures of variation. The fifth one, before we go into it, we need to understand the third basic numerical descriptor, which is the measure of relative position. And let's look at that in the next video.